You are listening to Climate Now. I'm James Lawler.
And I'm Catherine Gorman. And today we're talking with Pol Knops, the Chief Technology Officer and founder of a company called Green Minerals. 12 years ago, Pol had a PhD in physics and a career in converting waste products to energy and construction materials when he decided to create an entirely new product for a market that didn't really exist yet. Pol's plan was to develop a technique that turns carbon dioxide into a solid mineral that could be used as a feedstock in industrial and manufacturing processes. On the path to realizing this plan, he's become one of the world's top experts in the carbon dioxide removal technique called mineralization.
Mineralization of CO2 is the process by which carbon dioxide reacts with certain rocks and minerals to form solid and stable carbonate rocks, turning the CO2 to stone so that it cannot be re-released into the atmosphere. This process already occurs naturally, removing somewhere between 0.6 and 1.5 gigatons of carbon dioxide from the atmosphere each year. Pol's company, Green Minerals, is one of a handful of companies working today to create this process artificially.
Pol, welcome, and thank you so much for joining us.
Thank you. I'm very much delighted to be here indeed, yes.
I'd like to just jump into the science. How does your mineralization process work?
Yes, indeed, yes. Olivine is a mineral. It is an alkali mineral, and CO2 is an acid, carbonic acid. And you might remember from high school that acid reacts with base. And the olivine is a base, an alkaline material. It reacts with acids. So that's in essence the reaction.
So you use olivine to react with CO2, forming a new solid.
Indeed, yes.
So of all of the different, CDR possibilities, why do you find mineralization to be as compelling as you do? You are like the mineralization guy at this point.
Unfortunately, yes, indeed, yes. My background is physics, and the process is a bit physics, a bit chemistry, a bit geology. So therefore, I happen to be stuck in this process, but I quite like it because you are permanently binding CO2 and you're making valuable materials where you have the CO2 converted into that won't be released again anymore. So that's, and I think it's also being honest, is also partially the stubbornness indeed, yes, to keep on this track indeed, yes.
Pol has certainly been persistent. He's been working for over a decade to get Green Minerals off the ground.
He got the idea when he was working at a sewage treatment company using a high-pressure, high-temperature reactor to treat sewage. And he read that mineralizing CO2 would require high temperatures and high pressures, and thought the reactor for sewage could also work for CO2, which makes sense because CO2 is really just a different type of sewage, right?
Yeah, it's our energy sewage.
And he found an angel investor, and they basically cobbled together this reactor on their own in his basement. And then they needed more hands, they needed researchers, but they couldn't find any universities or institutions in the Netherlands that would support their work. So they ended up going to Belgium.
We ended up going to Belgium, to the University of Leuven. We met a professor over there, and he said, okay, that's a nice idea. If you supply the equipment, we supply the students, and then we can get things moving. We put it in the van from my brother, and we just drove over, and we installed it over there. And then I think 3 students did their thesis about that. One guy did his PhD about that. And that gave us, let's say, much more flexibility because we got much more access to university analytical equipment. After some time, we got a big project with ArcelorMittal, which is a major steel firm, and with Sibelco. That was the first time I would get some money out of this project.
And you're how many years in at this point?
I think something like 3 or 4 years.
Uh-huh.
So. Mm-hmm. And these 3 or 4 years were, of course, very tough because I was spending the savings of my children. I was doing some consulting in between just to pay the bills. And my angel investor, he paid for the equipment, but he didn't pay my salary. You have to remember, in Europe, getting venture capital is much more difficult. And so therefore, I was very glad we got a project with ArcelorMittal and Sibelco that speeded up these things. And also I learned that you need to have industrial partners involved, that you got to focus on not on your technology, but on the market.
So the first several years were rough, but it was a learning process for sure.
And then about, I think, 5 or 6 years ago, the project ended.
No.
Because the guy said it's not economically feasible. And then I said, yeah, of course not feasible, we're just getting started.
Pol decided that in order to make his process more attractive to investors, he needed to figure out a way to use the chemistry involved to create a product he could sell in a market.
We just were focusing at the academic stuff, at the chemistry indeed. And then we were slowly realizing we're making a product, we're making a powder, and the powder can be used for different uses.
What is the powder that comes out of this?
It is a mixture of magnesium carbonate and silica. And it's very small, very fine particles.
So then what'd you do? You had no more project, no more money. People were telling you it's not possible to do this.
Yeah.
And then what did you do?
I went to an incubator program because I thought, okay, I know the academics, I know the process, but I think we should better focus on the business side. And I had the hope that if I went to an incubator program, I got into some kind of ecosystem, I could form a team.
And how did that go?
The program was very good, so I learned quite a lot about venture capital and all these kind of things. But during that program, I happened to know the people from Heidelberg Cement for a long time. And then they came over to me and they said, okay, we got a proposal from the German ministry to look into mineralization. Do you mind helping us? And of course, as that's my business, and I said, yes, please. So the cement guy of Heidelberg and me put together a research proposal, really on one afternoon. That was on a Thursday. On Monday, we went to Berlin, presented the program.
And who were you? You were presenting it to whom?
To the German Ministry of Bildung und Forschung, Education and Research.
Okay, so Heidelberg Cement came to you. You put together the research proposal with them on a Thursday afternoon, and the following Monday presented it to the German Ministry of Education and Research. What did they say?
She said, okay, you proposed 4 years, make it 3 years. And she said, okay, you have to include German minerals. I said, but German minerals are not suitable. She says, that will be the outcome. And he said, go ahead. So we got 2.2 million euros.
Wow.
Out of blue indeed, yes. That was on a Monday. And then we went to the University of Aachen on Thursday. And of course, if you got then a budget from the German ministry, if you got Heidelberg Cement, I think the number 3 major global cement player. So then the doors at university opened. And we were able to get this research proposal, let's say, converted into the academic reel. So we were able within 1 week to sit with 5 professors together and to make it into work packages and these kind of things. So that was really a kickstart, yes. And it was by far the biggest mineralization program in the Northern Hemisphere, so that was quite a good start, indeed, yes.
So all this work, all this struggle, you lose your angel investor. You say, I can still make it work. You get into an incubator program, and then out of the blue, this cement connection calls you, and boom, a week later, you have 2 million euros and you're the biggest mineralization project in the Northern Hemisphere.
It was also, for me, it was complete. I was really shocked going in, and not a committee, not something, just I said, okay.
Just, here you go. Right. But okay, so now that was how many years ago?
That was 3.5 years ago, 3 years ago, yes.
Oh, wow. Okay. So 2018. And where has that struggle, perseverance, falling down, getting back up, where has that all led you to today?
Yeah, the project is almost finished. So that is positive. We have some results. So let's say something like concrete, these type of things.
Mm-hmm.
And I learned quite a lot. I realized that besides concrete, paper is an interesting market. If you make paper in Europe, there's about 6 million tons of lime used in paper manufacturing.
Right.
Concrete is, of course, a bigger market. Concrete is also, let's say, by its nature, a very slow process. Of course, you need to have certification and the validation.
So let's just to explain that, because I think that's very interesting. You would think that, wow, big market, concrete, let's just go there. But this certification is really important because, so can you just explain that for everyone?
Yeah, if you're making a new product in the paper industry, nobody minds if the paper, if after 1 or 2 years get bleached or something like that. And of course, most papers are used only for a couple of weeks. But of course, if you make concrete, you want to be bloody sure that your house stays there for 30 or 60 or 100 years. So, and you have all kind of, let's say, aging process to know what is happening in due time. But you see, first of all, the market is slow to respond to new things because it is already at a very big scale. If you come there with a product where you can make, let's say, at 1,000 tons per year, they don't take you seriously. And if you make 1,000 tons of year in the paper industry, you can already supply. Also, in the paper market, you can sell this type of filler for 100 euros per ton. But in the concrete market, I know the prices are lower because, let's say, typically cement is being currently sold for about 50 or 60 euros per ton. That means you cannot sell somebody which is making cement for twice as much as he is at the end of the day getting for his product.
Mhm.
So that means that you need a bigger scale, but also you need more earnings from the CO2. But in due time, I expect indeed that the CO2 prices will be higher, and then you can lower your end products indeed, yes. Paper is the first step to the market. If it will be the complete market, it will stick to 6 million tons of product in Europe. But I expect that will be the first market, and then from there, and there are also, let's say, other markets which you never thought about.
And it's clear that at this point you've refined your technique and have this product that can be incorporated into other end user materials like paper and concrete. But I want to get into the business side of things. How do you actually make this happen? Would these industries have to change how they make their product to incorporate the mineral powder that you produce? Or is it a one-to-one translation where your mineral product can replace existing feedstocks for the concrete or the paper that these companies are making?
The idea is one-to-one drop-in replacement, because then it's the easiest way to get into the market, and it will be very hard to make a new market and make a new product. In paper, there's quite some lime use, so basically it's the idea to replace the lime. They add lime to that for a few reasons. First of all, for the color, make it more white, but more importantly, to make it cheaper and to have better properties. And you see, the 6 million tons is already, I would say, a big market. And also the prices are much higher than in concrete. So therefore, is the idea just to, instead of use the traditional lime, use this material.
When we're talking about the paper product, how long does the CO2 stay in it? Is it until you recycle it again or reuse it, or is it just always trapped, forever trapped, sequestered there?
It is always trapped. Let's say you're making that into a different chemical form, you're making it into a carbonate. And therefore, this trapped, it only gets released if you heat the paper to 630 degrees. So let's say if you burn the paper. But then otherwise, you would have used other lime, which would also release CO2.
What does the business case look like? What are the costs?
The CO2, let's say, depending on the location, because it's also a commodity. If you be very close to fertilizer plant, you will pay something like 30 euros per ton.
30 euros. Okay.
But let's say if you're farther away or smaller amounts, it can go much higher indeed, yes.
Okay.
Yeah, so let's say you're buying 2 tons of olivine, let's say for 50 euros. So you're paying as a feedstock 100 euros. The CO2, let's say, at the beginning you need to pay for that for 30 euros. But eventually you get paid because the ETS price this moment is 50 euros per ton. And then on the other side, you're making, let's say, 3 tons, each worth 100 euros per ton.
Right.
So you have a gap between the feedstocks you're buying and the product you're making. Yes, 150 euros per 3 tons of end product indeed, yes. Yeah.
Well, that is a pretty significant profit margin then, I mean, at least theoretically. I guess the next question is, how far can you scale this up? You mentioned that 6 million tons of lime are sold currently in Europe for the purposes of paper production. I guess is the idea to completely replace that market?
Yeah, that means, let's say, you need to have 2 million tons of CO2 and 4 million tons of olivine if you want to replace all of this lime. That's feasible because CO2 is one coal-fired power plant already has 1 million tons of CO2 or 2 million tons of CO2. The global olivine production at this moment something like 8 million tons of olivines. So that's
Is the global market, is that annually?
Yeah, indeed, yes. But that's as the olivine mines, they are supplying to the steel industry for a completely different purpose.
Okay. And CO2 production from a single coal plant, you said one coal plant will produce
1 or 2 million tons of CO2 as typical value indeed.
Okay. So is this sort of a niche solution then? I mean, because if you're basically able to take the CO2 from one coal plant, but obviously we have a much bigger problem than one coal plant.
Let's say in respect to the problem, it is a niche indeed, yes. But I envision more that at the end you have a paper mill which emits something like 40,000 tons of CO2 for running their gas-fired boiler, and then use that CO2 to make their own filler. And then let's say a typically paper mill uses about 100,000 tons of lime. So then you will need probably half the amount of CO2 they're emitting already from their natural gas-fired power plant. So you see, I don't, let's say, expect that you build one or two big installations for making this kind of material. I envision more that you ship the olivine to the paper mill and that you there make your own filler at the side of the paper mill with the CO2 they're producing already from their power plant.
But that being said, even if it is sort of localized to the paper plant, it doesn't change the total sequestration potential of the technology in Europe, right? I mean, we're still talking about 6 million tons, which seems quite small compared to other proposed carbon dioxide removal technologies like carbon capture storage, CCS.
So let's say from a climate point of view, this is small beer. But of course, you have to remember paper is only one market. The concrete is a much, much bigger market. And in contrast with CCS, you can start it at small scale and learn and scale up. And CCS has got the disadvantage. First of all, you're only depending on the CO2 price. And secondly, your first step is already 1 million tons. You can't do CCS for 50,000 tons. And of course, the paper mills, they're typically orientated at historic locations, very close to cities, inland, these kind of things. So therefore, you're right, and the paper is a niche. On the other side, 2 million tons of CO2 sequestration is already, I think, globally with CCS is about 6 million tons. So there's already quite a lot.
You make a good point. It's still good to remember that all of these technologies are still quite nascent. Yeah. And as you mentioned before, there are other markets besides paper and concrete.
I have one more question about the economics of carbon capture and mineralization. You hear that there are many companies that are trying to get to, quote, net zero, unquote. They're in desperate search of negative emissions that are certified, where it's clear that carbon is actually being sequestered. And your process provides that reliable, permanent CO2 removal in that you're producing an actual powder that one can see or an actual, solid material.
Yeah.
Why not seek funds from those corporations, that are already spending money on this so they can claim negative emissions, credits essentially? Or have you done that?
I haven't done it yet because I first need to make the paper.
Right. But wouldn't they be interested even without the paper? Their interest is CO2 capture.
Indeed, yes. I think you're right. I think it would be interesting. But then, let's say, if you have 1 ton of CO2 you want to dispose, then you're grinding up a mountain where you get 2 tons of olivine, and then you're having 3 tons of end product where you need to dispose to a landfill. From climate change, it makes sense indeed, yes. But from environmental, you have all kinds of geoengineering discussions with grinding a mountain, putting in a landfill.
Right.
And let's say if you're making paper, I can very simply say, okay, people are buying paper. They're using lime for that. They're already having a quarry for lime. Close to lime quarry, leave that as it is, and open an olivine quarry. And so you see, you avoid all kinds of geoengineering discussions. Economically, it is more feasible.
Building a new olivine quarry simply for the use of sequestering CO2 didn't seem very environmentally friendly to Pol, unless it was replacing a lime quarry. But instead of digging out the olivine, some companies are trying what is called in situ mineralization, in which the carbon dioxide is captured and injected into suitable rock formations underground, where it then reacts to the rock in the same way, permanently changing its composition.
This doesn't result in a saleable commodity, but since companies are spending big money these days to offset their emissions, there is money in simply capturing and injecting carbon under the ground. And that's exactly the type of project that CarbFix and Climeworks launched in September 2021. Which is the world's first direct air capture to mineralization facility. Although direct air capture is not very efficient and is extremely expensive, the project does save by being located in Iceland, directly over a huge reserve of basaltic rock that is perfect for mineralizing CO2. Also in the nascent stage is research on mineralization using mining tailings or leftovers to reduce environmental impact. While all of this work is still in a developmental phase, including Pol's work, one important note is that the potential of mineralization is theoretically unlimited, given the vast amount of available basaltic rock in the Earth's crust. So perhaps one or more of these processes might take off in the coming years.
Could be. That is it for this episode of the podcast. You can check out other interviews, watch our videos, and sign up for our newsletter at climatenow.com. And if you want to get in touch, email us at contact@climatenow or tweet at us at WeAreClimateNow. We hope you'll join us for our next conversation.